All right, so today we're going to cover the main topic for today is getting into electrostatics. Okay, but before we get into that, we can cover the Stokes theorem problem in the last module. So let's go to that. Vector math. Okay, so what was it was the Stokes theorem, right? Okay. All right, was it this one? Let's see. Okay. Let's see. We did line integrals, then we did Stokes theorem. All right, Stokes theorem was for the field. Let's see, I'm trying to recall which problem it was. Okay, it was a radius 1. So I believe it was this problem. Yeah? Okay. This is the vector field 0x, and then you're asked to calculate the line integral. Now we did the entire circulation around here, right? I'm seeing a lot of blank stares. We only did 0 to pi over 2. Yeah, I just want to start with what the problem is. This was the problem, right? Okay, this was the problem, and I told you to calculate the circulation of this vector field over this quarter circle. Okay, and there were several parts to it. We had to calculate the circulation along. We had to calculate this line integral. We had to calculate this line integral, and then we had to calculate this line integral. There were 3 parts to it, right? And then we came up with an answer. Then, by using Stokes theorem, there's an easier way to do this problem. And the easier way to do this problem was to take the integral over this entire area, okay? And then we take the integral of the vector field, the curl of the vector field. Let's just remind ourselves what Stokes theorem is, okay? If I ask you to calculate the circulation around a closed surface, there's 2 ways you can do that. Okay, and in a test or homework, you have to decide which one of these 2 ways is easier. The Stokes theorem says both ways are equally valid. The first way you can do it, okay, so suppose you have a vector field A, okay, and then you have the surface within that vector field, and you're asked to calculate the total circulation around S. Now remember, circulation is the tendency for that surface object to rotate in the counterclockwise direction. The first way to do it is by doing the line integral. If we go all the way around this contour and we add up all the tangential vectors along this line, that will give us the total circulation. So the way that's expressed mathematically is A dot dl. dl is the tangent vector at each one of these points along the line, and A is the vector field. So A dot dl is the component of the vector field that's tangent to that line. You see this arrow? You see how this arrow is tangent to the vector, tangent to the surface? what you're doing is at each point along this line, you're finding the component of the vector field that is tangent to the surface. The vector field can point in any direction, right? You're only interested in the component that's tangent to the surface because that's what causes that surface to rotate. All right, so that's why it's A dot dl. Now, the other way you can find it is by integrating the curl. The curl del cross A is the tendency at the tendency of A to rotate at any point in the space. So effectively, what we're doing is del cross A. If we integrate del cross A over this entire surface, we're adding up the curl at every single point in this space. All right, the curl at this point where my mouse is, that's the tendency of that particular point to rotate. If I integrate the curl over the entire surface, I'm adding up the tendency to rotate along that entire surface. And that will give the circulation, the tendency of that entire object to rotate. Does that make sense? Sort of? Okay. So in this example problem that we did last time, okay, it's a line integral. It says line integral, but we actually did the entire circulation. So there's the surface looks like this. It's bounded by this semicircle here, and then there's a line here and a line here. So it's a quarter circle. The vector field that you're given is f of x, y is equal to 0, comma x. You can see this vector field's plotted here. It gets larger. The arrows get larger with larger x. And you're asked to find the circulation. Right? Now, so this particular problem, I think what you're going to find is your homework problem might actually be easier than this one. This was a tricky one. The reason why it's tricky is because we were given the vector field in Cartesian coordinates, but this particular problem is easier to do in cylindrical coordinates. Why is this one easier to do in cylindrical coordinates? Because we have the quadrant of a cylinder, right? These lines that we're integrating across, right? We have to integrate along this line here, along this quarter circle, and then along this line. These can be easily described in cylindrical coordinates. This line here is constant phi. This line here is this quarter circle here is constant r. Constant r, variable phi. This line here is variable r, constant phi. This line here is also variable r, constant phi. So this line integral can be nicely done in cylindrical coordinates. But we're given the vector field in Cartesian coordinates. So what we can do is a transformation. The way we did the transformation, we followed the formula for Cartesian to cylindrical transformations. And this was in the notes. All right, and when we did that transformation, we found that the field had an r component and a phi component. R cosine phi sine phi times r hat times r cosine squared phi times phi hat. So that was the first step. And then what we did, again, I'm going over this fairly quickly. We went over it in more detail last time. We did each of these three line integrals. The first line integral is going across this quarter circle. The second line integral is going from here down to here, and the third line integral is going from the origin out to here. So this is the first step here. We did step 1 here. So once we figured out what the vector field is, actually the rest of the problem, though it's a little bit tedious, it's not terribly difficult. And the methodical way of doing it is this. For each one of these lines, we have to define what that line is. All right? This is true whether you're in Cartesian, cylindrical, spherical coordinates, whatever. First thing you have to do along each line is you have to define some type of equation for that line. So what defines this line here? This quarter circle in cylindrical coordinates. How can you define that? Yep, the phi variable is going from 0 to pi over 2. And what's the equation for that line? Isaac's got it. It's r equals 1. The equation for the line here in cylindrical coordinates is just r equals 1. Because everywhere along this line, the radius is 1. Right? This is the reason we did in cylindrical coordinates in the first place. Because it makes it very easy to define these lines. So this line here is r equals 1. So that's what we have here. We define the line, r equals 1. That's a good question. It's something that you will get better with experience, but in this problem, the logic that you use is, okay, the lines that I'm going to integrate along, are those better defined in Cartesian coordinates, or are they better defined in cylindrical coordinates? This particular problem, you can see that you're integrating along a circle. If you're integrating along a circle, then polar coordinates or cylindrical coordinates is more appropriate. Spherical coordinates would be if you're doing a line integral that's or a surface integral where you're going across surfaces of a cylinder, or like a wedge-shaped, that's a wedge-shaped element or a cone-shaped element. Those are good for spherical. I should tell you, this problem can also be done in Cartesian coordinates. What would the equation of the line be if we were in Cartesian coordinates? The equation of a circle in Cartesian. No, I got it. X squared plus y squared equals r squared. So in this case, x squared plus y squared equals 1 is the equation that defines a circle in Cartesian coordinates. Right? Yeah. So the ones, you'll see your homework problems that you're given, I'm actually telling you which coordinate system to use. Well, by the way, about the homework, I intended to assign it last Wednesday. I didn't get to it, unfortunately, so that gives you some extra time. It's going to be posted today, and it'll be due 1 week from today. So, all right. So the equation that defines this line here, this quarter circle, is r equals 1. Now, once we define an equation for the line, we can then find what dl is. Once we find out what dl is, we can find out what a dot dl is. That's the process. We figured out an equation for the line, r equals 1. And then if we differentiate that, then dr is equal to 0. We need both r and dr for when we figure out dl. The definition of dl in cylindrical coordinates is dr times r hat plus r d phi times phi hat. Remember the differential length elements in cylindrical coordinates. Make this a little bit larger so you can see. dl is equal to dr times r hat, r d phi times phi hat. Now what we do is we substitute these values here, the equation of the line. Wherever we see r, we put 1, so this would become 1. Wherever we see dr, that becomes 0. So that's why this term basically goes away. So this term would go away because dr is equal to 0. And this r is equal to 1. All right, so a dot dl, we have our equation for a. This is our vector field. A dotted with dl. You multiply the r components together, and so you get r cosine of phi, sine of phi, dr. And remember, dr is equal to 0, so this goes to 0, plus the phi terms. So this is your phi hat term, r cosine squared of phi. Multiply that by r times d phi, and you get this here, r squared cosine squared of phi d phi. All right, and then once you have this is just in terms of phi, because r squared is equal to 1, and so this just becomes a simple integral then. All right, again, at the risk of being very repetitive, the process was this. We first had to convert this to cylindrical coordinates, so our vector field is now in cylindrical coordinates. For each one of these line integrals that we're doing, we first find an equation for the line. Once we find the equation for the line, then we can figure out what the dl vector is. The dl vector is going to be different depending on what line you're working on. That's the key point. Then you figure out a dot dl, and then you integrate through the limits. In the case, the limits here was phi is going from 0 to pi over 2. Because you're doing the line integral from here to here. All right. So the next line here, I'm not going to show the solution here. I would like to everyone to just look at it and tell me. This is a line that's going from this point to this point, back to the origin. What's the equation for this line in cylindrical coordinates? You got it. Phi equals pi over 2. That is the equation for the line. At every point along this line, phi is equal to pi over 2, right? Right? On the third line, yeah, we'll get to that in a second. Good. So if the equation for this line is phi is equal to pi over 2, what's the limits of integration for this line? R is going from 1 to 0. Now the key point I want to make here, the limits of integration is 1 to 0. It's not 0 to 1. Because the direction, you see the arrow here? The arrow is going from r equals 1 to r equals 0. If it was going up, it would be from 0 to 1. Exactly. Yeah, these are all the key points. Yes, you had a question? Yeah, we are going counterclockwise. So notice that the limits of integration for the first line was phi equals 0 to phi equals pi over 2. So we were going counterclockwise along that circle. Now this one is going from r equals 1 to r equals 0 at a constant phi. And what will be the equation for line 3? What's the equation that describes this line here? Not quite. It'll be similar to what the equation for this line was. Are we at constant phi or constant radius? Phi equals 0. That's correct. At everywhere along this line, phi is equal to 0. So the equation here is phi equals 0, and what are the limits of integration here? R equals 0 to 1, correct. All right, so that's really the key here, figuring out what the limits of integration are and figuring out what the equation is. As you can see along line 2, phi equals pi over 2 and d phi is equal to 0. The limits of integration r is from 1 to 0. I circled that because it's 1 to 0, not 0 to 1. All right, so you figure out what dl is, and then you figure out what ad dot dl is, and then you integrate. And you come up with 0 here, and you end up having 0 here as well. And if you think about it, this actually makes sense. The integrals along line 2 and along line 3 are equal to 0. Why? Look at this. Just look at this visually. What do you notice? What do you notice about the vector field along this line here? It's parallel to it, true, but the value of it is 0. F of x comma y is equal to 0 comma x. So that means the magnitude of the vectors along this axis here basically equals 0. There's no force. There's no vector field there. It's a 0 vector field. So of course the integral of that vector field along this line is going to end up being 0. Look at how the vector field is defined. F of x, y is equal to 0 comma x. When x is equal to 0, what's the value of the vector going to be? 0 comma 0. 0 vector. if you look at this plot, you can see this, like the arrows are long here. They get shorter as you go towards the x equals 0 axis. And by the time you get here, there's no, yeah. So along this line, there's no, the value of the vector field is 0. How about along this line? It's not 0, but the line integral along here is 0. Why? Yeah, yeah, exactly. Yeah, see, you guys are thinking. The vector field is perpendicular to the line that you're integrating across. So dl is going to point in this direction from left to right. The vector field is pointing up, so they're orthogonal to each other. When you do that dot product, a dot dl, that dot product is 0. That's why you end up getting 0 as a line integral here, 0 as a line integral here. The only place where it actually has a non-zero value is along this line here. Excellent. Okay. We figured out those line integrals, and we found out that the first line integral was pi over 4, the other ones were 0, and that left us with pi over 4 as the total circulation of that semicircle. Now, we do the same problem. We can figure out the same answer by doing the other half of the Stokes theorem, which tells us we did this line integral here. Now we're going to do this surface integral, and we should get the same answer. So the first thing we have to do is find the curl, and then we integrate the curl over the entire surface. So this is del cross A, and then we will take the double integral of that. All right, we figured out what ds is. ds is perpendicular to the surface there. Right, this is along the xy axis. So the vector that's perpendicular to the surface points along the z-axis. That's why this says z hat. So finding the del cross A, finding the curl in cylindrical coordinates involves this nice lengthy formula that you'll find in the notes in that table. I left these blank because it turns out that those parts of it turn out to be 0. So I didn't even bother writing them in because we were in a rush. There's only a z component, and when we solve for the z component, we end up finding, after a little bit of math here, ugly math, we find out that the curl of A is just 1 times z hat. All right, and if we integrate the curl, along this quarter circle. What are going to be the limits of integration if I want to integrate this quarter circle? What are the two variables we're going to integrate? Phi and r. That's correct. What's going to be the limits of integration for r? 0 to 1. Correct. And limits of integration for phi? 0 to pi over 2. Exactly. So this was the curl. We figured out what ds was. They're both pointed in the z hat direction, so we take the dot product of those and we get this. We get a scalar quantity here. The limits of integration are just what we talked about. R equals 0 to 1, phi is equal to 0 to pi over 2. And then we come up with pi over 4 here. Same answer as the line integral. Does this help clarify a little bit? The formula for the curl, yeah, it's in the table, so it's here in the notes. There we go. Why did it do that? It's on slide 62. The curl of A in cylindrical coordinates. So don't worry, I will give you that. I will give you those formulas on the exam. In the homework problems, I actually tell you to solve it both ways, so that you get practice doing line integrals and surface integrals and volume integrals. On the tests, I haven't decided yet. You know, like I think after doing some practice problems, you should feel comfortable figuring out which one's easier to do. Or if you start doing one and you see that, oh my gosh, this math is crazy, then you try the other one. Developing that intuition is actually important to know which one you want to go. I'll tell you a very simple rule of thumb, right? Very simple rule of thumb is this. For this particular problem, in order to figure out the circulation, we had to do 3 line integrals, right? If we wanted to figure it out using the double integral of the curl, we only had to do 1 integral, right? So obviously it's easier to do it the second way. But what if what if it was the entire circle instead of a quarter circle? How many line integrals would we have to do if it was the entire circle? Yeah, just 1, right? Yeah. So in that case, it might be easier to do the line integral. I'm sorry? Even if you used, yeah, if you found the curl and then you integrated, if you did the area integral, it would still be 1 integral, right? But you have to calculate the curl, right? So if it was going all the way around the circle, I would say just do the line integral once. But if it's something like this where you actually have to do 3 line integrals, then I would say much easier to go the other way. Minimize the number of integrals you have to do. All right. Good. Any other questions on this module? Okay. So like I said, the homework is going to be posted tonight. It'll be a bunch of problems on the divergence theorem and